Hello, today we are going to discuss relativistic quantum mechanics. So, before entering into the main topics, which means Klein Gordon equation or this Klein Gordon equation, uh, also called relativistic Schrodinger wave equation, Dirac's relativistic equation, and their continuity equations and their inadvocates. So, first we know the relationship between the relativistic energy and relativistic momentum. So this one is very very important. So we already know. So energy E square equal to P square C square plus M naught square C power 4. This is the relationship between the relativistic energy and relativistic momentum P. So let us spend little bit of time to derive this equation. So energy E is equal to mc square, Einstein mass energy relation, where m is m naught divided by root of 1 minus v square divided by c square. So substitute this value here. The energy term E equal to m naught c square root of 1 minus v square divided by c square. So this is equation number 1 and this is equation number 2. This equation I'm going to derive both sides square, okay? Then square this equation, both sides, equation number 2. Then we'll get E square 1 minus V square divided by C square M naught C square. Sorry, M naught square C power 4. This is equation number 3. Now we know the linear momentum P equal to mv. Relativistic momentum, if you want relativistic momentum, can use CV divided by C square. In so for M, we need to use C divided by E divided by C square. Therefore, relativistic momentum P equal to EV divided by C square. So this is equation number 4. Just square this equation. P square equal to E square V square C power 4. Then this equation P square C square equal to E square V square divided by C square. So here I split C square here, C square here. Total C power 4. So this is equation number 5. Substitute equation number 5 and equation number 3. I mean, sorry, not substitute. Just add equation number 3 with equation number 5. Okay, these two things. Just add these two things. Then you will get the P square just addition only, right? P square C square plus M naught square C power 4 equal to C square, sorry, E square V square divided by C square plus E square 1 minus V square divided by C square. Okay. So this one and this one going to cancel after simplifying this one. Okay. Remaining we got only E square. So E square equal to P square C square plus M naught square C power 4. So this is our relation between relativistic energy and relativistic momentum. This is very, very important. Now we are going to enter into the our main concept, that is non-relativistic quantum mechanics. So sorry, I mean non-relativistic quantum mechanics. By using this non-relativistic quantum mechanics, we discuss a lot of physical problems. This non-relativistic quantum mechanics equation is this one, Schrodinger equation, d square psi plus 2m divided by h cross square e minus v wave function psi equal to 0, or else this one we can write like this, h psi equal to e psi. Here the Hamiltonian of the system Hamiltonian h minus h cross square divided by 2m dou square divided by dou x square plus potential energy. Here the Hamiltonian function is the non-relativistic Hamiltonian. Hamiltonian. So by using this equation, we solved many equations like one-dimensional potential, well, barrier, um, step potential, like this. So here one of the important information is quantum mechanics developed so far does not satisfy the requirement of special theory of relativity, because it is based on the non-relativistic Hamiltonian. By using this wave equation, we discuss physical problems with I mean first order in time, second order in space coordinate. So here, if you observe here, so you can't understand like this. Just enter here Hamilton I am using here. After you will understand easily. H cross square divided by 2m dou square divided by dou x square plus v to a function psi, right? Replace energy operator I h cross dou by energy with respect to the time, right? Time. So if you clearly observe here, the time coordinate I mean this one. Time coordinate is the first order coordinate. Time is the first order coordinate. If the space coordinate is here, if you observe the space coordinate, this one is a second order, right? Space coordinate is the second order. So now we are discussing non-relativistic quantum mechanics. In general quantum mechanics, we are dealing with non-relativistic quantum mechanics, right? So right now, our topic is relativistic quantum mechanics. If you consider a system, any problem is a relativistic case, relativistic quantum mechanics case, there is one contradictory there in non-relativistic relative case, especially Schrodinger wave equation. If you clearly observe here, there is no space-time symmetry. First point. Second point is, if you want to solve a relativistic quantum mechanic problem, we should consider space-time symmetry must and should. So, which means space-time requirement of relativistic, I mean relativity. These difficulties are suggested in two ways to obtain the relativistic wave equation. Either you should convert the space coordinate into the second order coordinate to first order coordinate, or you should convert time coordinate into the second order coordinate. Okay, so basically I'm saying what I'm saying, you should maintain space time symmetry, which means both space coordinates and time coordinate must be in the same order, whether it should be first order or second order, doesn't matter. Okay, uh, space time symmetry is required. So first, this problem is highlighted by the Schrodinger. He suggested the two ways to obtain the relativistic wave equation. First point is here, he suggested to use a relativistic Hamiltonian for a free particle in a place of non-relativistic case. That is the first suggestion. Second suggestion, what he suggested, uh, try to find a both coordinates, space and time coordinate in the first order equation. So try to find the first order equation both space and time coordinate. So space and time coordinate both should be in the first order coordinate. So Klein and Gordon working on the first problem, which means the first point, they are trying to use a relativistic Hamiltonian for a particle in place of a non-relativistic case. Then they got one equation. So let's go and discuss that equation first. So this is the main important introduction of the relativistic quantum mechanics. So this is a non-relativistic Schrodinger equation. Here the space coordinate is second order derivative, time coordinate is first order derivative. So we should convert these coordinates, space and time coordinate should be one coordinate. It is better to go only the first order coordinate. Second order derivation equations are very difficult to solve. So which is why Dirac derived this equation first order coordinate. Or you should replace Hamiltonian, non-relativistic Hamiltonian with a relativistic Hamiltonian. These are the two ways to get this equation, this Schrodinger wave equation into space-time symmetry. So that is the main requirement of the relativistic case problems. So first we need to solve Klein Gordon equation by replacing uh, non-relativistic function with the relativistic Hamiltonian function. So the non-relativistic Schrodinger equation was obtained by just replacing uh, momentum operator, energy by energy operator, right? So we already know that equation. So just I'm going to rewriting that equation. D square psi plus 2m divided by h cross square e minus v to wave function psi equal to 0. So this is non-relativistic Schrodinger wave equation. Now we need to apply a Schrodinger solution, first solution. So this solution is carried by the Klein and Gordon, which is why we are calling this equation Klein Gordon equation. So they are trying to put this Hamiltonian, yeah, in place of Hamiltonian, they are try to put the relativistic Hamiltonian, which means they are using relativistic energy relation. We already discussed this one. E square is equal to c square p square plus m naught square c power 4. So this is equation number 1. Here a m naught is the rest mass of particle. Replace energy and momentum by the respective operators. You will get this equation. H cross square dou square divided by dou t square equal to minus c square just momentum operator h cross square del square plus m naught c power 4. This is equation number 2. We know, right, energy operator and momentum operator. So momentum operator is momentum p equal to minus I h cross d by dx or dou by dou x. Energy equal to I h cross d by dt. Just replace this operator here, you will get this equation. So here I'm going to allow this wave equation. I mean quantum state. I am going to define wave function like this. This is our quantum state. Here the time also there. This is our quantum state. Okay. So I'm going to use this type of wave equation here. So our equation is h cross square d square psi divided by dt square r comma t space and time. Okay. H cross square c square del square psi of r comma t plus m naught square c power 4 psi of r comma t. So this is the famous equation known as Schrodinger relativistic wave equation or Klein Gordon equation. This is very famous equation in relativistic quantum mechanics. So if you clearly observe here, space time symmetry is there. This one dou square by. So if you want to clear, just I'm going to write this one like this. Let's wait. dou square divided by dou x square. So here space coordinate and time coordinate both are there in space time symmetries. So this is the first requirement of relativistic case. So this equation is derived by the Klein and Gordon with the help of Schrodinger solutions. Klein Gordon equation, or we can call this one Schrodinger relativistic equation. Equation. Okay. So or else this equation I'm going to write like this: del square 1 divided by c square, dou square divided by dou t square, to wave function psi equal to, I'm forgetting to write these factors, just write uh, r comma t into m naught square c square divided by h cross square wave function psi r comma t. So Klein Gordon just rearrange this equation like this. Okay, this function, the famous function, this one D'Alembert operator. We're going to use call this one D'Alembert operator. D'Alembert operator square psi of r comma t equal to m naught square c square divided by h cross square wave function r comma t. So this is also the rearrange equation of Klein Gordon. Okay. Here the delta is represented D'Alembert operator. This delta is the D'Alembert operator, which is relativistically invariant. Therefore, this equation is relativistically invariant if psi is transferred like a scalar. So here the wave function, the plane wave, this plane wave is represented this equation r comma t equal to exponential I k dot r minus omega dot t. Okay, is a eigenfunction of both energy and momentum operators with the eigen values of h cross omega and k h cross respectively. This is eigenvalue, energy eigenvalues. This is the momentum eigenvalues. So therefore, just we are going to rearrange this equation again. E square, this equation E square equal to c square p square plus m naught square c power 4. This is the relativistic energy and the momentum relation. So just use this information eigenvalue equation. Let us try to find some points here. Energy value h cross square omega and momentum value c square h cross square k square Okay, h cross square k square plus m naught square c power 4. Here we got one important information. H cross omega equal to what here? Plus or minus root of c square h cross square k square plus m naught square c power 4. So here we need to understand one important point here, that is, if you observe this equation clearly, energy have two terms. One is positive, another one is negative. So we know about especially in non-relativistic quantum mechanics, many times we observe the energy factor in the positive term. We know that value. But here this Klein Gordon equation suggests this equation energy eigenvalues can have both positive and negative values. The Klein Gordon were not able to give the consistency explanation of the negative energy. They give the explanation about the positive energy, but they are unable to give the what is the negative energy of the system. Klein Gordon equation. Some important contradiction points are there in Klein Gordon equation. If you want to go by point, so here maybe after deriving the continuity equation, we'll get more points. Right now, we're going to end this video here only. Okay, this is the important relation. So Klein Gordon explained positive energy successfully, why they are getting positive energy. So they are unable to explain what is the negative energy of the systems. So this is all about Klein Gordon equation. So if you look at these equations properly, uh, just we start begin with relativistic energy and relativistic momentum. Then we try to explain what is needed for relativistic quantum mechanics. So first we took Schrodinger wave equation. That Schrodinger wave equation, mainly if you observe here, the space and time coordinates, two different coordinates. So space is there in second order derivative, time is there in first order coordinates. So especially in our latest quantum mechanics, we need to use the space and time symmetry property. So therefore, they try to rearrange this equation into the time and space coordinates. Okay, with help of Schrodinger, Klein and Gordon both are Klein Gordon both are try to derive this equation. So which is known as this famous Klein Gordon equation. Uh, they're taking one important point, just they are replacing non-relativistic Hamiltonian place. They are going to they just replace the relativistic energy value, I mean relativistic Hamiltonian value. Then they rearrange the equation, they got the uh, space and time symmetry required property of relativistic problems. So remember this one. So after deriving continuity equation, we'll get more points. I mean, how this Klein Gordon equation is explain the positive and negative energy, density function, current density, all these things. If you want to derive the uh, continuity equation from Klein Gordon equation, you need to derive the continuity equation of especially in content equation in relativistic quantum mechanics. So we already know content equation in a non-related case. We already discussed. So right now I'm going to, I mean, next class I'm going to derive um, content equation from relativistic Schrodinger wave equation. Okay, thank you.